Hello, I'm Jan-Erik Kallhammer. I'm going to present sensing in adverse weather conditions. So why is adverse weather performance important? Well, what happens to self-driving cars if the weather turns bad? And we need to resolve this issue unless we all move to Arizona, California, Bay Area, Israel or similar places with very rare cases of adverse weather. Sensors in a typical setup for level 3 plus driving, and level 3 plus means we allow the driver to take his or her eyes off the road within the defined operational design domain, ODD. And that means that the system must be capable of handling all such situations within the ODD. Sensors typically consist of cameras, radar and LiDAR, and they have various field of view resolution and range requirements. Current sensing limitations are in tunnels, and maybe limitations due to radar multipath reflections, camera dynamic range limitations at tunnel entrance exits, darkness, lack of visibility of essential features, heavy rain, snow, fog, where most of the sensors we currently use degrade severely or even fail completely, and low friction, which is it should influence the self-driving car's behavior. Adverse weather conditions, it's important to remember that signal levels depends on the amount of obscurance in the atmosphere, and use cases determine the amount of degradation. How severe conditions are we going to design for? Is it adverse weather conditions that happens once every 10 years, or every year, or every month? How often are we going to allow a self-driving car to not be able to operate properly? And that will determine the specification of the ultimate system. And it's also important to recognize that sensor improvements and sensor fusion results interact. So we need to train the CNNs, the convolutional neural networks, with relevant adverse weather conditions. The picture here of the car front, in the grille you see a rectangular, that's the radar dome, and in the center of the grille you have a camera, and both are completely iced up after driving in wet snow conditions. Even if you have the sensors in a more protected area, like on the roof in this test car with the LiDAR on the rightmost picture, you still got a lot of wet snow, and that meant that you had no signal in the forward direction. Radar is often considered to be all-weather proof. And radars are important, but they are neither sufficient by themselves, and they are not completely all-weather proof. They are much better than cameras and other sensors, but they also suffer. I just showed a picture of what happens with the radar dome, maybe blocked by water or snow, but you also have other problems are poor resolution for classification, may have multipath backscattering or ghost objects through spraying water, and finally orientation of objects is not a learnable feature. There are challenges with camera data, and there may be essential features that current sensors miss. So can you see the oncoming vehicle here in this image? Probably not. So the image processing challenge is immense in this case. Even if you combine it with image, even if you combine images in LiDAR, you have some issues. And here we have some example of processing results, and the model here is trained solely on clean data without distortions, and we measure the number of cars detected. In the topmost image here, we have LiDAR only detection, where only 1 out of 9 cars were detected, clearly insufficient for level 3 plus. In the second image here, we have image-only detection, where only 5 out of 9 cars were detected, still insufficient for level 3 plus. In the third image, we have the proposed fusion architecture, where all 9 cars were detected, and then we are on the way to meet the level 3 plus requirements. If you want to read more about this comparison, you can check up the paper in the reference in the bottom of this page. This work was conducted under the DANCE project, an EXA project with European funding. So input to the new sensors was degraded information from fog, rain, snow, dust and smog, and we fed it into new sensors consisting of gated cameras, shortwave infrared LiDAR and multiple input, multiple output radar. Fed it into a new processing unit that consisted of both signal enhancement and fusion based on convolutional neural networks, and then we restored the information to counter the degradation information from the diverse weather conditions. One of the cameras I mentioned was gated imaging. Active gated imaging is not so familiar, so let's explain that one. First of all, you have the scene. It's illuminated with a very short laser pulse. And you have a shutter on the global shutter on the camera, and the shutter is initially kept closed. So the reflections from the backscatter in front of the object you're interested in is not captured because the shutter is closed, and then you open the shutter at a certain when the laser lights that travel a certain distance, and then you get an image slice, and then you close the shutter again to only capture at the defined distance. And in this way we avoid backscatter and only capture the slice of interest. And to illustrate that more, I have 3 different images here. To the left we have a near zone up to 20 meters. In the middle we have 20 to 40 meters, and on the right we have 40 to 60 meters. And you can see then how the illumination moves further and further away. The reason also other parts are slightly visible is due to some ambient light. It wasn't completely dark when we recorded this thing. Please note the effect on the retroreflective traffic sign when we move the illuminated zone further and further away, or the captured slice further and further away. Cameras at night. Standard passive cameras are essential, but they have performance limitations. So if we then take a standard camera here with auto iris, you can see that there are some folks crossing the road, and if you actually look carefully you can see there are some folks crossing the road further down. But the image processing challenge is tough here. If you really pay attention, you actually see that there is some pedestrians on the sidewalk, but it's very hard to see whether they are going parallel to the road or on the way to cross the road. If you go into the gated image, instead, it's easy to see all the pedestrians we talked about here. If we take the same camera set and move it into a fog chamber with artificial fog, and in this case the visibility was 50 meters. So to the left we have the standard camera, and we have on the side of the tunnel there is some mannequins to symbolize pedestrians, and it's very hard to make them out in the standard camera image. You may see the one that's closest to us here, but it's very hard to see the one furthest away close to the car in front. In the gated camera it's much easier to discern them. In the same fog chamber we have here to the left a column of smaller images where the top image is a regular camera, in the middle is the gated camera, in the bottom is the thermal camera, and the big image is the point cloud output from the LiDAR, and this red speckle close to the vehicle is reflections from the fog particles in the air. So you see that fog is a very challenging situation. We used this gated camera to a novel advantage to reconstruct the depths. So we took 3 different slices of images, slightly overlapping, and we fed them into a neural network that then reconstructed the depth. So we got a 3D image down to an accuracy of 5% within the reconstructed range. And the network was trained using LiDAR depths as ground truth data, which is much more accurate. But it's important to remember that range and resolution requirements are connected, and that's why LiDAR resolution is often insufficient, and why we are looking at the cameras which has generally higher resolution, spatial resolution. Range determines how fast you can drive in automated mode. You cannot drive faster than you can stop within the distance you can sense. And resolution determines how small objects can be classified, and that's usually considered to be one of the challenging road use cases is road debris, and it's usually considered to be 10 centimeters tall, which is the limit of what you can drive over in road debris. And range without resolution is not enough, so the minimum resolution is determined at target range. Or if the resolution sets the limit, then the range, effective range, is determined by your resolution. As an example here, if I take the Velodyne HTL64, which is the rotating LiDAR become very well known from the early Google cars. It has a measurement range up to 120 meters. It has a vertical field of view of 26.9 degrees, which gives an angular resolution of 0.42 degrees. If I put it in the equation, I get a vertical point separation of 0.9 meters. That gives maximum 2 spots on the height of a tall SUV. What then makes things more complex in this analysis that we generally are after free space detection, drivable area, and that eases the requirements somewhat, and we can also work with varying vertical resolution. But that also makes it a bit more complex. If I take an Alpha Prime, the 128 beam rotating LiDAR from Velodyne, it has a nonlinear distributed beams and with a minimum vertical resolution of 0.11 degrees. It gives a minimum point separation of 0.23 meters, which is much better. But it also means that it's not the same all over the scene. So if you then have roads like San Francisco type roads or whatever, where your vehicle is not always in the same horizontal plane as the object in the question, it becomes even more complex then to analyze it. This equation gives the number of photons received from a LiDAR, and it depends on a bunch of parameters which I won't go into here. It's important here, I want to get your attention to, is the last factor called K here. It's an optical attenuation in the light path. So we can say it's the adverse weather effect. And that can easily be 50%. And if you have a 50% attenuation, it can be compensated, for instance, by increasing the emitted power, by doubling it. It of course assumes that your eye safety allows you to double the power, and you would have to then increase the complexity of cost of your emitted power. But there are ways to compensate for adverse weather. As a summary, AD sensor performance in adverse weather. Standard cameras are insufficient. Radar are degraded less but lack resolution for classification. LiDAR are degraded by backscatter, and eye safety requirements limit how much power you can emit for 905 nanometers, the most common wavelength. Of all the sensors examined in this project, the gated camera had the highest potential in bad weather, but that means yet another sensor type in an AD vehicle. Summary of the AD sensor requirements. 3D sensing closely connected to the quality of the perception. Actual depth resolution requirements are unclear. They need to be sufficient to support classification, but they may be lower than previously assumed. 3D information using depth reconstruction from gated imaging appears sufficient, and that could alter the use and requirements of LiDAR to ground truth generation, meaning you may not need it in your serial vehicle. There are some gaps that needs to be closed before we can transfer into serial automotive development. First, we need to have designs that unites the best aspects of camera and depth sensing. We need to further validate increased performance potentials of automatic recognition and adaptation of sensors to prevailing weather conditions. We need to work on gated imaging and the trade-off between various sensor combinations and their requirements. And we need better bad weather simulation data, especially for active sensors. And we need to extend this adaptation capability to higher processing levels, fusion and higher. I'd like to acknowledge Dr. Werner Ritter, Manager Vision Enhancement Technology at Mercedes-Benz, the coordinator of the DENS project and also a contributor to this presentation. The dance project consortium consisted of 16 partners listed here from 6 different countries, also listed here. It lasted from June 16 to end of February 2020, had a budget of 14.5 million euro, of which 4.2 were European funding and 3.1 million was national funding. If you need further information of the dance project, you can check up this website. And with that, I thank you.